Okay, welcome back everyone. So for this video, we're going to start talking about limits and infinity. So a couple of questions to motivate where we're going to go. So what we'd like to ask is what happens at points where the function is undefined? So we've seen a couple of examples of that so far. So we've had some places where the function was defined but the limit existed, other places where the function was undefined and the limit didn't exist. Then we can also ask what happens when the value of the function goes off to infinity, and also what happens when the x value goes off to infinity. Okay, so remember the definition of limit that we've been using so far. So what we've said is if f is defined for every x value near some number a, except possibly at a itself, and if we can ensure that the f is as close as we like to some number L by taking x as close as we need to a, but not equal to a, we say that the function f approaches the limit L as x approaches a, and we write it as the limit as x goes to a of f of x equal to L. Okay, now here's an example of a limit that does not exist. And the reason is because that as x gets closer and closer to 0, the value of this function grows without bound. So in this case, we'll say that the function is uh, going to infinity at x equals 0. And for everything that we're going to do, infinity is not a number. It's more of an abstract concept. So when you have a case like this, we'll say that the limit does not exist. So formally, if x gets closer and closer to a, f is growing arbitrarily large, we will say that the limit as x goes to a of x is infinity. And if f of x is negative and grows arbitrarily large in magnitude, as x goes to a, the limit is going to minus infinity. So whenever I say large, I mean large in magnitude. So something like conceptually 100 billion, we'll say is large. If I'm talking about small numbers, I mean numbers that are close to 0. So minus 1 over 100 billion. So minus 1 over 100 billion, 1 over 100 billion are small, 100 billion or minus 100 billion are large. And as I was saying, these limits do not exist because infinity is not actually a number, so it doesn't fit with the definition that we've been using so far. But in these cases where even though the limit doesn't exist, we can still discern some information about what's going on, so we still talk about these limits even though they don't actually exist. And then if we wanted, we could also use the same kind of definition that we've been using for left and right-sided limits so far. And these lead us to what is called a vertical asymptote. So a vertical asymptote is going to be any place where at least a one-sided limit is infinite. So if you had the right side limit went off to infinity, but the left limit went to 7, we'd have a vertical asymptote at that point. And those asymptotes are written as the lines x equals a, because the expression x equals a defines a vertical line. Okay, so some arithmetic operations for infinity. If you take infinity and you add or subtract a constant, you still have infinity. If you take infinity and you multiply it by an infinity, you get infinity. If you take something very close to 0, so some small number, and you power it up an infinite number of times, you get 0. If you add infinity to infinity, you get infinity. If you multiply infinity by a constant, you get plus or minus infinity depending upon the signs of everything involved. If you take infinity and you power it up an infinite number of times, you also get infinity. You could think about that as an infinite application of the second rule, multiplying infinity by itself. If you take 0 and raise it to the power of k for some value k, you get 0 if k is bigger than 0, but you get infinity if k is less than 0. So remember, if you had k with something negative, that would be rewriting the expression as 1 over 0 to the k, which would give you something infinite. And k to the infinity is going to be infinity if k is at least 1, and 0 if k is in between 0 and 1. So if you take a number bigger than 1, you multiply it by itself, you get something bigger, do that an infinite number of times, and it will grow without bound. And if you take a number smaller than 1 and multiply it by itself an infinite number of times, you're eventually going to get 0. Okay, and then some division. So if you take 0 and divide it by some non-zero number, you obviously get 0. If you take 0 divided by infinity, you also get 0. Whenever you take a constant, no matter how big that constant is, and divide it into infinity, you get 0. So with some of these for divisions, think about it as the constant is your net worth and the infinity is the net worth of, say, Jeff Bezos. You'd wind up with a massively large number in comparison. We'll treat that as infinity for simplicity. If you take a constant and divide it by 0, you get plus or minus infinity depending upon the signings of the numbers involved. If you divide infinity, if you take infinity divided by k, you also get a plus or minus infinity, and same if you divide, if you take infinity divided by 0. Now, there are a couple of arithmetic operations that we haven't seen here. One is infinity minus infinity. We have infinity plus infinity, that's infinity. But infinity minus infinity could actually be anything. It could be plus infinity, it could be minus infinity, it could be something in between. And the same is also true with infinity divided by infinity. You could wind up with infinity, you could wind up with minus infinity, you could get 0, you could get something else entirely, and we'll see some examples of these. Okay, so what we'd like to do is go and find some infinite valued limits. So here I have a plot of the function 1 over x squared minus 1, and what we can see is that the denominator is going to be 0 at plus or minus 1. The numerator is not 0 at either plus or minus 1, and that's leading to these vertical asymptotes here. So some of the examples we've had so far, we've had limits where the denominator is 0, but the numerator is also 0, and we've had that the 0 in the numerator is getting canceled out by the 0 in the denominator. Now what we could have is the denominator is going to be 0, but the numerator isn't. And whenever you have that showing up, you're guaranteed to have a limit that goes off to infinity, and we just want to figure out whether it's plus or minus infinity. Right, so here we have is that the left limit at minus 1 is plus infinity, the right limit at positive 1 is infinity, the right limit at minus 1 is negative infinity, the left limit at plus 1 is minus infinity, and we'd just like to see why this is the case. Okay, so for the first one. So we have the left limit at minus 1 of our function 1 over x squared minus 1. And when we're doing these, as we've done typically, we want to first factor. So we'll factor our denominator, which is a difference of squares, into a sum and difference. So we'll get the limit as x goes to minus 1 from the left of 1 over x minus 1 times x plus 1. Now what we can see here is that as x goes to minus 1, this x plus 1 factor is going to go to 0. But the numerator is non-zero. So now all that remains is we just need to figure out what sign everything is going to be. So our numerator is going to be positive. This x minus 1 factor, as x goes to minus 1, is going to be something negative. And as x goes to minus 1 from the left, this x plus 1 factor is going to be very small and also negative, because the x values are to the left of minus 1. So what we'll have is a positive number divided by a negative number here, so minus 2, and we also have this factor of very small negative numbers. So we have a negative times a negative in the denominator. The denominator will be positive. We're dividing that into a positive numerator, so our limit is going to be plus infinity. Okay, so next we'll do the right limit at minus 1. And I'll just do the two limits at minus 1. If we wanted, we could do the two limits at plus 1, and we get kind of the same analysis. Okay, so here again, we'll factor our denominator as a sum and a difference. And this time what we'll have is this x minus 1 factor is still going to go to minus 2, but this x plus 1 factor will now be small positive numbers because we're going to have x values that are to the right of minus 1, and we're going to add 1 to that. So we'll get numbers there that are small and positive. Our denominator will then be something negative times something positive, so overall negative. Divide that into a positive number and we get a negative, so we get minus infinity. So notationally, this is one way that you could kind of imagine what's happening. We have a positive numerator, we have a negative factor in the denominator, and we're multiplying it by small positive numbers. So we have a positive divided into something negative, and the denominator is going to 0, so we get a minus infinity. Okay, so one other question that we could ask is, suppose that we have this piecewise defined function. Let's go and find all of the vertical asymptotes for f of x. So what we're looking for is all of the places where our denominator is heading to 0 and the numerator is going to be positive. So in this first block, we have the denominator is going to be 0 at x equals 0 and also x equals 1. Now this part of the definition only applies for negative x values. So this x equals 1 part is never going to appear. But as we come at 0 from the left, we're going to have that this factor, just x, is going to be heading to 0. The numerator is going to be just 1. So our function will be heading off to infinity at the point x equals 0. And in fact, it'll be plus infinity. In the second block, the denominator is always 1, so we're not going to pick up any vertical asymptotes from that. The third block, we have tangent of x. Now, whenever dealing with trig functions, it's usually best to rewrite it as, rewrite whatever you have in terms of sines and cosines. And tangent is sine divided by cosine. So what we're asking is, are we going to get any vertical asymptotes from this on the interval 1 to pi? Well, cosine is going to be 0 at pi over 2. And pi over 2 is going to fall within the interval 1 to pi, so we will get a vertical asymptote at pi over 2, because sine of pi over 2 is 1, so the numerator there will be 1, the denominator is heading to 0. And then the last block, the denominator is only 0 at x equals 2, but x equals 2 is clearly not bigger than pi, so we're only going to have the vertical asymptotes x equals 0 and x equals pi over 2. And that's nicely given in this plot of the function. So what we'd have is the one-sided limit that heads off to plus infinity, and then we have limits that are heading off to plus and minus infinity around x equals pi over 2. Okay, so then one thing that we can just kind of quickly note about these limits where the function goes off to infinity, just because the denominator is heading to 0 doesn't mean that you're going to have a vertical asymptote, or that the function is heading off to infinity. Because the examples that we've had leading up to today, we've had something like in case 1. So the numerator and denominator are both heading to 0, as in this case x goes to 2, but they're going to cancel each other out, and you would wind up with a limit that wasn't infinity, and in this case you would get 1/4. In the second case, the denominator is heading to 0, but the numerator isn't. So whenever you see something where the numerator heads to something non-zero while the denominator goes to 0, you're going to have either plus or minus infinity. Okay, so let's go back to this plot from a moment ago. So one thing that we'd already asked is, where does the function value head off to infinity? And we said that was at 0 and pi over 2. And now what we want to ask is, what happens as the x value goes off to infinity? So what it looks like from this, as x goes off to minus infinity, the function seems to be settling in around 0. And as x goes off to plus infinity, it's somewhat hard to see from the plot, but x is going towards 1. And we'll see why this is in a moment. Okay, so what we'll say is that if x is defined on some interval a to infinity, so the function is defined for all values bigger than some value a, And we can ensure that f is as close to some number L by taking x sufficiently large. Then we'll say that the limit as x goes to infinity of f of x is L. And we could do the same thing for x going to minus infinity, and we would get the limit as x goes to minus infinity of f of x is m. And what we'll say in this case is that the line y equals L or y equals m, context depending, is a horizontal asymptote. So we had a vertical asymptote before, now we're going to have a horizontal asymptote. Same idea, except it's a horizontal line, so we get y equals some number. And in these cases, these limits do actually exist, because the limits are settling in on a number. Okay, so let's go through 9 examples. So the first one is pretty straightforward. If you take the limit as x goes to either plus or minus infinity, doesn't matter, of 1 over x, that is 0. Because your denominator is getting arbitrarily large, and we'd said from our rules for doing divisions, we have a constant divided by infinity equals 0. Now here what I'm doing with the infinity is I'm kind of cheating a little bit with notation, and I'm writing it as k divided by infinity. When you were doing homeworks or worksheets or tests, you should not ever do that. You should just say that the limit, just that the limit is 0. It's really not proper notation to write infinity in a problem because infinity is not really a number. But I was just doing it at the beginning to make the notation just for simplicity. Okay, then the second one. So what we want to find is the limit as x goes to plus infinity of x divided by the square root of x squared plus 1. So what's happening here is if we went to go and put in, if we said as x goes to infinity, our numerator is going to infinity, and our denominator is also going to infinity. So this is very much like when we would have in the last 2 days limits where the numerator is going to 0 and the denominator is going to 0. And as we said at the beginning, when you have infinity divided by infinity, you could wind up with anything, in the same way that when we had 0 divided by 0, we could get anything. So whenever you have an infinity divided by infinity case, we need to go and start doing some algebraic manipulation. So what we're going to do first is we're going to factor. So we're going to particularly factor an x squared out from both of these terms underneath the square root. So if I pull an x squared out, I can rewrite what's underneath my square root as x squared times 1 plus 1 over x squared. So it's the same thing, I haven't changed anything. Now what we're going to do is we can split this square root apart. So in general, the square root of a times b is the square root of a times the square root of b. So again, we haven't changed anything here. And what we want to do is we now want to simplify the square root of x squared. And what we need to note is that because x is bigger than 0, the square root of x squared is just x. And we'll see that it matters whether or not x is positive or negative. Okay, so we've taken care of that. We now have an x in the numerator. We have an x factor in the denominator, so we'll just cancel those. And we're left with the limit as x goes to plus infinity of 1 divided by the square root of 1 plus 1 over x squared. At this point, we can go and use our quotient rule, because as x goes to infinity, the denominator's not going to go to 0, and it's also not going to be infinity anymore, which is very convenient. And then we're going to be able to switch the order of taking the limit with evaluating the square root, because 1 plus 1 over x squared is not going to be 0 as x goes to infinity. In fact, it's going to be something positive, so our power rule for limits allows us to make that switch. Then we have the limit as x goes to infinity of 1 plus 1 over x squared, and as x goes to infinity, 1 over x squared goes to 0. So in this case, our limit is going to be 1. Similarly, we could go and find the limit as x goes towards minus infinity. So with this one, the analysis is going to be almost identical, except for this line. So before we said that because x was positive, we could rewrite the square root of x squared as just x. Now we're looking at the limit as x goes to minus infinity, so x is going to be negative, and here we're going to write the square root of x squared as minus x. So the reason for that is this. Over here, we're going to take some negative number and square it. That'll give us something positive, and we're going to take the square root. So we'll say that also gives us something positive. On our right side, x is negative, so we'll have minus something negative, which will also give us something positive. For example, if x was minus 3, and we took minus 3 and squared it, we would get 9. We would then take the square root of that and get 3, which is minus minus 3. Okay, so again, then we're going to do the exact same steps. We would have x divided by now minus x. We'll cancel the x's, and we'll just get the exact same thing as before, just with a minus sign out in front. So we follow the exact same procedure, and we get a final limit of minus 1. Okay, so now let's go and look at the limit as x goes to infinity of 3x cubed minus x squared plus 2. So as I'd said, infinity minus infinity, it could give you anything. So it could give you infinity, it could give you minus infinity, it could give you something else. Here, what we're going to do is we're going to say, well, let's go and try and factor things. So what I'm going to do is multiply and divide everything by an x cubed. So in other words, factor x cubed out from everything. And when we do that, what we see is inside the parentheses, we get this 3 minus 1 over x plus 2 over x cubed. And as x goes to infinity, the 1 over x and the 2 over x cubed are going to go to 0. So in other words, our limit is just going to be the same thing as the limit as x goes to infinity of 3x cubed, which is plus infinity. Another way to see it is to just kind of think about this with some numeric examples. So suppose that we had, to make this a little bit simpler, we had the limit as x went to infinity of x cubed minus x squared. Well, first suppose x was 10. If x is 10, x cubed is 1,000, x squared is 100. So you'd have 1,000 minus 100, 900. Okay, so what we're working with got a decent bit bigger. Then when x is 100, you're going to have 100 cubed, which is 1,000,000, minus 100 squared, which is 10,000. Well, you have 1,000,000 minus 10,000, that's 990,000. So things are getting bigger. And what we'd see is that in general, as x goes off to infinity, x cubed minus x squared, it's going to basically be x cubed. And that's the idea that we had here. Okay, and if we did this limit as we went towards minus infinity, we'd have the same idea. It's just now we would have the limit as x goes towards minus infinity of 3x cubed. Well, take a negative number and raise it to the third power. You've still got something negative, and x is going to minus infinity, so you're going to wind up with minus infinity for the final limit. Okay, and that leads us to this nice theorem. So whenever you have a polynomial and you find the limit as x goes towards plus infinity of some x to the n, you always get infinity. And if you find the limit as x goes towards minus infinity of x to the n, it's plus infinity if n is even and minus infinity if n is odd. Clearly because in the odd case, we'd be multiplying a negative number, an odd number of times, which will give you something negative. And then as we'd said a moment ago, if you ever have the limit as x goes towards plus or minus infinity of 1 over x to the n, that is always 0. And again, please don't write it as 1 over infinity, because it's not really correct. Okay, and then if we have the limit as x goes towards plus or minus infinity of some polynomial, all we need to do is concern ourselves with the leading term. So in this case, we would just be able to rewrite the limit as x goes to plus or minus infinity of this polynomial as the limit as x goes to plus or minus infinity, depending on what the problem is, of an x to the n, which will be plus or minus infinity depending upon the sign of everything involved. Okay, so now let's see what happens if we have a rational function. So we'll take the limit as x goes to plus infinity of 2x squared minus x plus 3 all over 3x squared plus 5. And what we can do is we can do the same kind of trick. We can go and factor out an x squared from both the numerator and denominator and then cancel various pieces. So we'd be able to cancel this x squared factor from both numerator and denominator, And then we have a 2x squared over x squared, that's clearly 2. We have an x over x squared, that's 1 over x, and so on. Now what we have is a denominator limit that's not going to 0, it's not going to infinity. Our numerator limit's also not going to 0 and not going to infinity, so let's use the quotient rule. Now what we have is the limit as x goes to infinity of 2 minus 1 over x plus 3 over x squared, and it's all divided by the limit as x goes to infinity of 3 plus 5 over x squared. And using what we just said, those limits of 1 over x to the n's are going to 0 as x goes to infinity. So we just get left with 2/3. Okay, so then we could change things a little bit and take the limit as x goes to infinity of 5x plus 2 and divide it by 2x cubed minus 1. We'll do the same thing. We'll factor out an x cubed from everything. And when we do that, we have a limit as x goes to infinity of 5 over x squared plus 2 over x cubed, and it's all divided by 2 minus 1 over x cubed. Well, our denominator limit's not going to be 0, so let's go and pull out the quotient rule. Our denominator limit is just going to be 2, because we have 2 minus 1 over x cubed. The x cubed is going to 0 as x goes to infinity. But our denominator limit is going to be 0. So in fact, the entire limit is going to be 0. So next, we want to find the limit as x goes to infinity of the square root of x squared plus x, all minus x. And what we have here is something that is an infinity minus infinity kind of expression, because the square root part is going off to plus infinity, and then we also have a minus x as x is going to infinity. And one of the things we mentioned at the beginning is that infinity minus infinity, you could wind up with anything. You could get plus infinity, minus infinity, 0, something else entirely. And we had one example of that so far when looking at polynomials. So maybe we'd like to go and do what we've done so far, which is try and factor things. And if we factored it, we'd get down to this line. And what we'd have is x as x is going to infinity times this part in the parentheses. The unfortunate part is that what's in the parentheses is going to 0, and infinity times 0 is also not a clear arithmetic operation. Again, that also wasn't in the prescribed list of arithmetic operations for dealing with infinity. And what we'll see in about 2 weeks or so is that this really isn't any easier to deal with than infinity minus infinity. So we'll do something else. Instead, what we'll do is we'll multiply by the conjugate. Because what that'll do is it'll change what's going on with this square root, in effect. So what we have is we have the square root part minus something else that's going to infinity, but now what we're going to get is a square root of x squared plus an x outside the square root, and that'll be much easier to deal with. And also conveniently, our difference of squares gives us x squared plus x minus x squared. The 2x squareds will nicely go away, and then we'll do the factoring trick. So we'll write it as x squared times 1 plus 1 over x squared, and then we still have that plus x sitting down in the denominator. Because x is going to be positive here, we can then go and write the square root of x squared as just x, and then cancel. So we have an x that is common to every term in the denominator. We'll factor it out and cancel the x's away, which will leave us with the limit as x goes to infinity of 1 over the square root of 1 plus 1 over x squared plus 1. So again, at this point, we've done a lot of algebraic simplification. We haven't done anything with limit rules yet, and again, this is why you need to have pretty good algebra skills for doing limits, because the algebra stuff is really most of the problem. Okay, so now at this point we can say our denominator limit's not going to go to 0. Everything in the denominator is going to be positive, so we can go and use our quotient rule. And then nicely, we're also going to be able to use our sum and power rules to switch around the order of doing square root with evaluating a limit. And because the 1 over x squared is going to 0 as x goes to infinity, we get 1 over the square root of 1 plus 0, which is nicely 1, plus 1, so we have 1 over 2 for a final answer. Okay, so then as we've done so far, we could go and look at the limit as x goes to minus infinity, the same expression. And if we really, really wanted to, we could go and try and do the same kind of analysis, but it would be fantastic overkill. The reason for that is when we had the limit as x went to plus infinity, we had the square root part was going to plus infinity. And then we had minus x, and x was also going to plus infinity. But now x is going to minus infinity. So we have minus something going to minus infinity. This part is actually going to give us a plus infinity. And then we have the square root part is also giving us a plus infinity. So we have infinity plus infinity. And from our rules for arithmetic dealing with infinity, that's just going to be infinity. Okay, so one consequence of some of what we've seen so far is that whenever you have a rational function divided by a rational function, or sorry, you have a polynomial divided by a polynomial, so you have a rational function. So you're looking at a limit as x goes towards plus or minus infinity for a rational function. All you need to do is compare the biggest terms. So for one of the cases, we had the biggest term in the numerator was 2x squared, and the biggest term in the denominator was 3x squared, and we got a final answer of 2/3, because if you divide the biggest powers that show up, you would just get 2/3. And then for the other example that we had something with an x where the biggest power in the numerator was x, the biggest power in the denominator was 2x cubed. And when you divide those two, you would get 1 over 2x squared, and as x goes off to plus or minus infinity or whatever, you would get 0. And that's exactly what we had, and that's not a coincidence. So whenever you're doing a limit as x goes to plus or minus infinity of a rational function, you can just do the limit as x goes to plus or minus infinity of the biggest term in the numerator divided by the biggest term in the denominator. Okay, so then the last example that we have is we want to find the limits as x goes to plus and minus infinity for this function f. Now this isn't a polynomial, but it's kind of close. There's the square root part though that makes it not a polynomial. So we're going to need to do the kind of analysis that we just did. And then we also want to state any horizontal asymptotes if they exist. Okay, so we have this square root, and what we'd like to do is factor out an x to, or we'd like to factor out an x cubed from everything. Because what we could see, so the rule of thumb with this is to say, okay, what is the biggest power of x that we see sitting here? Well, in the numerator, it's x cubed. In the denominator, you'd be tempted to say it's x squared, or sorry, x to the 6th. But it's x to the 6th sitting underneath a square root. And the square root more or less has the effect of dividing the power in half. So you'd have an x to the 6 over 2 or an x cubed. You also have an x cubed here. So what you'd de facto have is that the biggest power of x showing up is x cubed, and we'd like to go and cancel off an x cubed, and then that'll help us be able to solve this. Okay, so we'll go and try and factor out an x to the 6 from underneath the square root. That'll give us an x cubed. So we'll do the same kind of trick. We factor out an x to the 6 from each term underneath the square root. We get a square root of x to the 6 times 16 plus 1 over x to the 6. And then we write it as a square root of x to the 6 times the square root of 16 plus 1 over x squared. Here, because we're looking at the limit as x goes to plus infinity, square root of x to the 6 is x cubed, so we write it as such. Now what we have is the limit as x goes to plus infinity with an x cubed factor sitting out in front for both numerator and denominator, which we can then cancel. So we can cancel those two away and then pull out our quotient rule and say we have the limit as x goes to infinity of 4 plus 1 over x cubed, and as x goes to infinity that 1 over x cubed goes to 0. In the denominator, we have the limit as x goes to infinity of 2 plus the square root of 16 plus a 1 over x to the 6, and as x goes to infinity, that 1 over x to the 6 also goes away to 0. So we would have 4 divided by 2 plus the square root of 16, or 2 over 2 plus 4. So 4 over 6, which is 2/3. And that'll tell us that the line y equals 2/3 is a horizontal asymptote. Okay, so now we'll do the same kind of thing, but for x going to minus infinity. And because the analysis is basically the same, I'm just going to go and look at the steps that will change. And really, here the only step that changes is saying that the square root of x to the 6 is minus x cubed. For again, the same reason. X is negative, so we'd need to write as minus x cubed. So the only difference in this problem to the last one is that the plus sign down in the denominator becomes a minus sign. And when we account for that, we do the same kind of thing. We take the x cubes, we cancel them away. We then go and use our quotient rule, and what we'd wind up with is 4 all divided by 2 minus the square root of 16. So 4 divided by 2 minus 4, so 4 over minus 2, which is minus 2. So that tells us that y equals minus 2 is a horizontal asymptote for this function. Okay, so that gives us a good basis for looking at limits and infinity, so places where the value of the function goes off to infinity, and also where the x value goes off to infinity. So there will be a worksheet on this content sitting in WoW Courses, so please do that and turn it in by tomorrow, and there will be a homework due coming up in a couple of days. Okay, and I will see you in the next